All right, so let's go ahead with section 4.3. And this section is translations or transformations um, in a sequence. Right, up till now, we have been talking about, uh, we've been giving you uh, a, a polygon or a quadrilateral triangle. And we've been giving you algebraic expression or description, and then we've been uh, saying, okay, well, what happens after we give you this one transformation, and then you map it or you figure it out. From here, uh, we're going to say, okay, well, what happens um, after, what happens when we provide you with multiple transformations? Uh, and we're going to give you the triangle, we're going to give you the polygons, and then you figure out what transformations occurred. So, um, so here we have uh, three polygons, and the first polygon is the original one. It's the blue one here, and it's labeled. We'll just say it's polygon quadrilateral DHKR. The next one is green, and it's D prime. It's DHKR prime. That's what these little hash marks are. And then we have the third one is DHKR double prime. And from that, this kind of indicates that this is the original image, right? The original pre-image. Then the green one happened after the first transformation, and the D happened after the second transformation. So blue transformed into green, and that transformed into red. So the first question is, um, what does it mean to maintain distance, to preserve distance? Well, when it means to preserve distance is which kind of transformations preserve distance, and that means, well, when transformation is conducted on a figure, that all of the lengths, the segment lengths of that make up that polygon um, maintain the same length, right? So if a rigid transformation happens, right, whether it's a translation, uh, or a rotation, or a uh, reflection, one all that results in all of the lengths of all of the sides are the same. So they preserve distance. So that's what that means. All right. So that's the first we want to get out of the way. All right. So that just means a preserved distance. So if it ever goes under, if any of these shapes undergo a rigid transformation, one of those three aforementioned transformations, they all preserve distance. So just remember that. Okay. Well, the next thing that I want to go over is, well, let's look what happened when the blue polygon transformed into the green polygon. What happened, right? My question to you is, what type of transformation occurred, right? And if you're using Microsoft Paint or something like that, you can say, well, if I copy this image here and paste it, well, what happened to get from here to here? It's obviously not a translation. I can maybe even go to like transparent selection. Obviously not a translation, right? What happens if I invert and I rotate that and I flip it horizontally? That's what happened there. I just reflected it. Well, it looks like I reflected that image, right? Still transparent. Yeah, it looks like I reflected that image. Okay, so that's a reflection, and that's a reflection across the x-axis. And then what are some things that you could say that would prove that? As well, you could say that I have each individual point is equidistant from the line of reflection. Well, that works out pretty good um, because it's equidistant from the line of reflection being the y-axis, because d is, absolute value is 2 from the y-axis. H absolute value looks to be 4. So does K, and R's absolute value looks to be 1. That's a pretty good indicator that it was a reflection. right? The orientation just kind of flipped, right? But how do I absolutely, unequivocally recognize that that is indeed a reflection? Well, I can use the points, compare the points and how they changed, and then compare that to one of the algebraic expressions that I know that is a reflection across the y-axis. So let me do that. All right, I'm going to pull 2 points that are fairly different. I don't want to pull point D and then compare to point D prime, because they both have the absolute value for the x and the y-axis of 2. All right, because then I would be, because the two things that you're comparing when you're comparing 2 points is the absolute value of the y and the x, and then the polarity or the sign of the x and the y axis, or the x and the y value, whether it's positive or negative, if those change, right? So I call polarity because I'm an electrician, right? So anyway, so I'm gonna pick like K, right? So I'm gonna pick K here. I'm gonna make that a little thicker. Pick like K. I'm gonna pick this K value for my prime value, and then I'm gonna pick this K prime, because obviously you have to pick the corresponding letters or points. And so I'm gonna go ahead and mark my K value. All right, so my K values, my points for K, right, are gonna be my X value is -4, and my Y value is -2, -2. All right, and then my K prime, my X value is 4, and my Y value is negative. I said -2. It's supposed to be -3. No, that's right. -2. -2. I was right the first time. -2. Right. So now I evaluate how everything changed. I'll do that in black. Right. So my X value, so my absolute values of 4 and 2, those didn't change. Right. So I'm not going to flip my X and my Y values. Those are going to be remain the same. My X's and my Y's didn't change. Right. This is my X value and this is my Y value. Those didn't change. They didn't flop, right? If it would have been like a rotation or something, those probably would have flopped, unless it was a 90-degree or a 180-degree rotation. But these didn't flop. Now, if I looked at my Y value was negative, and it maintained negative. So I'm not going to change this. My X value was negative, and it became positive, right? So this indicates that it did change polarity. Don't be confused with the actual value, whether it's negative or positive, but this just indicates that it changed from negative to positive, or positive from negative. It changed polarity, right? So my algebraic expression would be x comma y. That's how every algebraic expression ever starts, right? For these transformations, yields -x comma y, right? And if I go up and I pull from my bank of algebraic expressions, I would go and I would find, oh, let me go ahead and close that because it might go up and find my reflection across the y-axis is right there. You see that it is x comma y is at -x minus y. The x coordinates change. It's a reflection across the x-axis, okay, or across the y-axis. It really doesn't really show that, but that's the reflection. This is a reflection across the x and the y-axis. If it was a reflection across the y-axis, the y coordinate would swap. Okay, so that is the first one. Okay, so now let's go ahead and just talk about the second one. Now, oddly enough, reflections and rotations are kind of hard to understand initially, and then transitions or translations are kind of easy to understand, but the translations are the hardest to kind of like nail down when it comes to discussing and coming up with an algebraic description, because For every other one other than a translation, you can use these generic terms for now. Translations, you need to be a little bit more specific because because it is expected that you identify the magnitude by which the transformation or the translation occurred, right? So the algebraic description for a translation, if you recall, is x comma y, right? Yields x plus delta x, and that plus can become negative, of course, comma y, comma y plus delta y, delta y. And then when you have it on this coordinate plane, it's easy to figure out that delta x and the delta y just by coordinate counting. Okay, so let's figure out this delta x, let's just use point D here, right? So my delta x is 1, 2, 3, 4, right? So my delta x here, just by coordinate counting, was x equals 4, right? So this part would be x plus 4. That's how much the x value changed when moving this point. And if I move 1 point over, all the other points are going to move by the same magnitude. Any point on this polygon is going to move by the same magnitude, right? And then how much do I need to move up? Well, I need to move up 1, 2, 3, 4. So coincidentally, my change in y value was also positive 4 because it went up, right? 4. Okay. So remember, y going that way is positive, or x going that way is positive, x going this way is negative. You can see along the axis how that looks, and then y going this way is positive, y going this way is negative, in case you forgot. Okay, so then my y was a change in 4, so it's y plus 4. Now that's all well and good, but say for instance, my first transformation took this y here, right? It took this green off of here, and it just like put it completely off the map, right? It was completely gone for whatever reason, right? And it's just like it rotated it completely gone, right? Off the grid. Close enough. Okay, completely gone off the grid, right? And all I have is this this object to go off of, and the coordinate pair that I got from applying this algebraic expression to the original image, right? So it gave me the algebraic expression, or it told me that it reflected across the axis, or more than likely, if it pushed it off of the coordinate pair, it's more than likely a reflection or a rotation or something, right? But it's like, hey, this is no longer on the coordinate plane, but I know these coordinates, right? But I still need to figure out what my delta x, my delta y is. Right, so remember that your delta, a change, and no matter what, like whether it's physics or geometry or any math, your delta is the change, and it's the change in it's always your final minus your initial, right? And in our case, our final object is the red triangle, and the initial object is the green one. Okay, so if we're going to find the change in our x value, right, we have the k to deal with. So we have to use k, and we have to use the k value, right? But it's going to be, we know the final is k double prime. And this could be any value, like any point number. It's like called k double prime. So it seems a little confusing, but of x. So that's just saying that it's the k value, right? The point K, and it's the X value of point K, right? Minus, and it's going to be minus the K prime value, the K point of the X value of the K prime. All right, so let's just fill in some values here. So this is the X value of K prime, so that's 8, right? We'll bring that down. It's just the X value, and that's 8. And we're going to be minus the 4, the X value of K prime, right? So that's just going to get put into here. It's going to be minus 4. So we're just going to, that goes in right there. Okay. And of course, that equals 8 minus 4 equals 4. And then you can see how that gets plugged in right there. The same value, the same value. So let's do it for y. All right. So my delta y is going to be the same thing, except the y is going to take its place. So it's going to be K double prime, but the y value minus K prime and the y value. All right, so we'll pull off K prime, and that just happens to be 2. That's my final value, minus, that says minus a negative 2, right? So it's going to be minus a negative 2, which is minus a negative 2. And if I take minus a negative 2, right, that's going to be plus 2, right? So that's the plus equal signs there. So minus a negative 2 is 2 plus 2, which equals 4. And then you can see that that goes right there. So it's algebraically the same, right? So just so you know, that's the other way that you can figure out what the delta x and the delta y are, aside from coordinate counting. You can use the delta equals the final minus the initial of whatever point, and you're pulling the x values and whatever point of the y values. Just make sure you're using the same points. You can't use like d over here and then k over here. That won't work. Okay, so hopefully that works. And if you guys have any questions, please let me know.